Welcome to the video on taking derivatives of natural log functions. We're going to finish with some of the more complicated examples that we didn't get a chance to do in class on Friday, so that way you'll be able to answer some of the homework problems that I've assigned for this weekend. First, let's just recall the definitions for the derivative of a natural log function. Remember that if you have the function y equals the natural log of x, well, then its derivative with respect to x is going to be 1 over x. It gets more complicated when the natural log is part of a composition of two functions. And that's that second rule that was in your notes. It's ln u, where u is another function of x. This just means you have to use the chain rule. So you would take the derivative of the outer function. The outer function is the natural log, so you would still do 1 over u. But then you'd have to multiply that by the derivative of u, or u prime. And some textbooks will just write it like that, u prime over u. Okay? Both of these need to be made into flashcards. Both of these need to be studied and memorized so that you can take derivatives of natural log functions with some ease in time for the AP exam. I would say that the second one is the one that I usually study because, like I said, the ln x, this only works, this rule is only true if you're taking the natural log of a single variable, and that single variable is the variable that you're differentiating with respect to. So ln x, if I said, y equals ln theta, and I took the derivative of y with respect to theta, the answer would still be 1 over theta. It's if you put something more complicated in the natural log function. Even if the thing that's more complicated is just a constant in front of the variable, you have to consider the chain rule. Okay, and we did a couple examples like that in class, some of the more basic ones. Now I'd like to start on page 59 of your notebook, and I'd like to look at some of these derivatives. So we've got y equals the square root of ln x. Okay, so we want to look and see, well, what's happening here? We have two functions. We have an outer function and an inner function. So this is going to be a chain rule problem. We've got a composition of two functions. Our outer function is going to be the square root. Our inner function is going to be the natural log. So to take my derivative, I'm going to take the derivative of the outer function. So the square root would be 1 over 2 times the square root of whatever is in the radical, so ln x. But then we've got to multiply that by the derivative of the radicand function, which is ln x, and that's 1 over x. So to simplify this into one fraction, the derivative is going to be 2x times the square root of ln x. Okay? Let's look at the next one. Now we have a trig involved in our chain rule. So same idea. I see it's a chain rule because I have two functions. I'm taking the cosine of the natural log of x, and I'm also taking the natural log of x. So in order to differentiate, I'm going to take the derivative of the outermost function, which would be negative sine, evaluated at the inner function, ln x, and then I'm going to multiply that by the derivative of that inner function, ln x. So together, as one fraction, we get the negative sine of ln x all over x as our derivative there. Okay, we'll do a couple more. Now, what if we reverse it, just to remind you of the mechanics of the chain rule? These are still the same two functions as in question 10, except now the outer function is the log, the inner function is the cosine. So we will take the derivative of the natural log first, because that's the outermost function. So we'll do 1 over cosine x, and then we'll evaluate it at the we'll multiply it by the derivative of the inner function that's being evaluated. And that would be cosine. The derivative of cosine is negative sine x. Now watch how nifty this turns out when you simplify it. Okay, so if you put it in one fraction, you get negative sine x over cosine x. But what is that really based on your ratio identities from trig? Negative sine over cosine is negative tangent. So the derivative of the natural log of cosine x is going to just be tangent of x. All right. Let's look at number 12. So now I've got two natural logs being composed with each other. So in order to take that derivative, we're going to first start with the outermost natural log. So its derivative is 1 over whatever's inside, so 1 over ln x. But then we've got to multiply that by this derivative, which is just 1 over x. So combined into one fraction, the derivative of the natural log of x is 1 over x ln x. Okay? Now, remember, we want to work smarter, not harder. So as you see in your notes, there's 3 log rules that you learned in pre-calc, and you may have also learned in Algebra 2, that can help us take some more complicated derivatives and make life a little bit easier. So recall these 3 log rules that are up on the top of this slide. Remember, if you take the log of a product, that's just going to be the same as the natural log, or any log for that matter, of the first term plus the natural log of the second term. If you take the natural log of a quotient, so a over b, that's the same as taking the natural log of the numerator minus the natural log of just the denominator. And finally, my favorite, if you have a natural log of a power, you can bring the exponent out in front and make it a coefficient times the natural log of just the base, ln a here. Okay. As I said, that's going to come in handy for these next couple problems we do, where we're going to simplify things. We're going to make a more complicated function easier to differentiate. All right, so let's look at number 13. We have the natural log of x sine x. So let's do this the direct way. Let's do it using the rules that we just learned in this section. We have a chain. We have a natural log as our outer function, and then we have as our inner function x sine x, which itself is a product. So we kind of have a double dipper here in terms of rules. We're going to use the chain rule first, and then when we take our inner derivative, we're going to need the product rule. So here we go. All right, so to take the derivative of this, okay, the outer function is the natural log, so our new rule says we just do the reciprocal of whatever's inside the log, so 1 over x sine x. But then we're going to multiply that by the derivative of x sine x, which is going to involve a product rule. So the derivative of the first function is 1, times the second function makes sine x, okay, plus the first function, x, times the derivative of the second function, which is cosine x. Okay, so if we write this all as one fraction, we get sine x plus x cosine x all over x sine x. If you want, you can actually simplify this, and I'm going to do that so that you see how it works the other way, the shortcut way. I'm going to take each part of the sum and put it over x sine x separately and kind of break this up into 2 fractions. And you'll see why I do that in a minute. So look what happens. In the first fractions, the signs cancel and I get 1 over x. In the second fraction, the x's cancel and I'm left with cosine over sine, which is just cotangent. So that would be the derivative of the natural log of x sine x. Now, let's do this an alternative way using the rule of logs. So I'm taking the natural log of a product. So we said that's the same as just splitting it up and making it a sum. So I can rewrite this function as the natural log of x plus the natural log of sine x. Now watch what I do. The derivative of the first function, ln x, is just 1 over x. Ooh, that looks familiar. The derivative of the natural log of sine x would be 1 over sine x times the derivative of the sine, which is cosine. Oh, look at this when I start simplifying things. We have 1 over x plus cosine x over sine x. Where have I seen you before? That's just cotangent. That's also what I just got in the last way of doing this. So the 2 derivatives match. I don't know about you, but the log rule is probably easier. But again, there's more than one way to do these things in this course. If you forget the log rule, or if you don't notice that in the heat of the moment, you can use that direct chain rule approach and still, with some simplification, get the same answer. Let's try another one to see where that's going from. So now this one, I've got the natural log of the square root of x squared plus 2x. All right, this is kind of a triple chain. The outermost function is the natural log. As we move further and further inside, it's the natural log of a square root. And it's not just the natural log of a square root, it's the natural log of a square root of a polynomial. So we're going to have to break this down one piece at a time in order to get the direct derivative. All right, so the outermost function we have here is the natural log. So we'll do 1 over whatever's inside the natural log. So it's the square root of x squared plus 2x. Now we'll take the derivative of the square root function. So we'll multiply this by 1 over 2 times the square root of what's inside the radical, so x squared plus 2x. And then we've got to multiply by the derivative of what's inside the radical, which is x squared plus 2x, and that derivative is 2x plus 2. Okay, so let's clean it up. It actually cleans up rather nicely. So the numerator becomes 2x plus 2. The denominator, you've got a 2. And then when you multiply things out, you've got a root times a root. They're the same radicand, so you can just drop the root. And you can get even fancier, and you can divide out the 2 everywhere, and you get x plus 1 over x squared plus 2x. And I think that would be the most simplified version of this derivative. All right. Now, was it a pain to do it directly? It depends on your definition of what's a painful derivative. If you go one step at a time, it's not really too bad, but I can see some people getting confused by the multiple chains that are going on and the multiple chain rules that need to be done. So instead, why don't we use the log rules? So how about we think about it this way? Instead of writing it as the square root of x squared plus 2x, why don't we think of it as the natural log of x squared plus 2x raised to the 1/2 power? By doing that now, we can take that exponent and send it right in front of the natural log and think of this as 1/2 natural log x squared plus 2x. Okay? That kind of gives us one less derivative we have to worry about, because that 1/2 now is just a constant. So it's going to pull through my derivative, and we'll just take the natural log of x squared plus 2x's derivative and multiply it by a half. Okay, so let's do that. So my derivative now will be 1/2 times, okay, my outer function is ln, so I'll take the reciprocal of what's inside the ln, x squared plus 2x, and then I'll multiply that by the derivative of the x squared plus 2x inside. Now look what happens when we clean things up. Multiplying through the numerators of these three fractions gets me 2x plus 2. Multiplying the denominators gets me 2 times the quantity x squared plus 2x, and you see that matches that step. If we want to go a step further like we did before, we can still take out that power of, or factor of 2 and get x plus 1 over x squared plus 2x. So again, as I said, really boils down to what your strength is and what you want to do. Here's one more that I'm going to do with you, and this one they only prompt us to use log rules, and I think that's a great idea, because if we used it directly, we'd have to use a quotient rule, we'd have to use a chain rule, we'd have to do a lot. But look what ends up happening. We've got y equals the natural log of x squared minus 1 over x squared plus 1 raised to the 1/2 power. We'll bring that in front, and now I have 1/2 the natural log of x squared minus 1 over x squared plus 1. But now look, I'm taking the natural log of a fraction, a natural log of a quotient. So I can say, really, this is 1/2 the quantity of the natural log of x squared minus 1 minus the natural log of x squared plus 1. Oh my gosh, that just made this so much easier because I don't have to worry about a quotient rule anymore. I can do this more with my sum difference properties of differentiation, and I can just differentiate term-wise and go from there. So let's take this derivative now. Okay, so the 1/2 again just stays in front because it's a constant. We'll start with the natural log of x squared minus 1. So we get 1 over x squared minus 1, and then we multiply that by 2x because that's the derivative of x squared minus 1. And then we have to subtract another fraction. That fraction will be the derivative of ln x squared plus 1. So we have 1 over x squared plus 1 times 2x again. Okay, so let's start cleaning things up. So we get 1/2 the quantity of 2x minus x squared minus 1 minus 2x over x squared plus 1. Okay? Now, we can distribute the 1/2 in if you'd like, because since I have 2 x's in the numerator, that's going to make life a little bit easier. So this ends up being x over x squared minus 1 minus x over x squared plus 1. Now, you may need to get this into one fraction. If that's the case, we're going to need common denominators. So we're going to kind of crisscross things. We're going to multiply the first fraction by x squared plus 1, and the second fraction by x squared minus 1. So now we have x cubed plus x minus the quantity x cubed minus 1. all over x squared minus 1 times x squared plus 1. When we distribute that negative sign into the second set, we end up with the x cubes will cancel, and we end up with just x plus 1 all over x squared minus 1, x squared plus 1. Okay? So there you have it. We actually could simplify a little more, because remember, x squared minus 1, that's a difference of perfect squares. So I believe the complete, simplified final answer is going to be 1 over x minus 1, x squared plus 1. Okay, that's going to be the derivative of that. Now I'm going to tell you right now, we'd still be doing this problem, and we'd probably make 3 algebra mistakes if we tried doing it directly. Because we'd have to do 1 over that big square root times the derivative of the square root times the derivative of what's inside the square root, which is a nasty quotient. So I think this one, yes, had a little bit of algebra involved, but the algebra wasn't messy. It was just really getting common denominators, okay, and a little bit of factoring at the end. So with that, try some of the homework problems that I assigned. I asked you to do numbers 1 to 17 odd, and they can be found on page, you have to go a little bit further in the notes to get to the homework section. You got to go all the way to page 62 for that. Okay, we can talk about these on Monday, and if you have any questions, feel free to ask. Thank you very much for watching.